Hi. A few months ago we posted a video on hydrogen detonation, and if you're interested in this general topic, you might want to take a look at that video because I go through some of the formulas, some of the principles. We have a lot of fun and we do some pretty interesting demonstrations. And today what I want to do is I want to describe another unusual type of explosive. And before I get started, I'm just going to reiterate the written warning that we give you at the beginning of the video. Even if you're comfortable with chemistry, when you're dealing with high energies and very fast conversion speeds, in other words, explosives, you have to be particularly careful. And so I would give you the advice that I do not recommend that anybody try this at home. Now, explosives in general can be divided up into several different types of groupings. There are low explosives and high explosives. Typical examples of low explosives are gunpowder, sulfur, charcoal, saltpeter or potassium nitrate, gasoline and air in your car engine. These explosives are classified as low because when you ignite them, the transition zone or the flame front moves through the material at below the speed of sound. Not necessarily 330 meters per second or 1100 feet per second, the speed of sound in air, but the speed of sound within the material itself. A high explosive, on the other hand, once you trigger it, has a transition zone or a shock front that moves through the material at above the speed of sound, supersonically, and forms what's called a shock front or a shock wave. Now, examples of that are TNT, nitroglycerin, RDX. And the major difference with a shock wave or a shock front is that because the heat can't distribute through the material as it's burning or transitioning, all of the heat is concentrated in that very thin, micron-thin shell of expanding reaction. And so the pressures and the temperatures within that shock front can be an order of magnitude, a factor of 10, higher than they are in a low explosive. Now, a low explosive can still produce a shock wave in air. If you contain it in a strong vessel and it reaches very high pressures, that vessel can rupture and produce a shock wave. But the underlying reaction that occurred to develop that pressure occurred subsonically. The faster a reaction is in a high explosive and the more powerful it is, the more brisient it is. It's sort of a loose product of speed and energy. And so, for example, nitroglycerin is very brisient. It's more shattering, more cracking than, say, TNT. Now, another way of dividing explosives is into the burning or the combustion type of explosive and the decomposition type of explosive. Again, examples of burning types of reactions are gunpowder and the hydrogen and oxygen that we burned a few months ago. This requires two components to get together, react, produce reaction products that are more stable, have less energy in them, and the resulting heat produces the energy of the explosion. In a decomposition type of reaction, all of the atoms that are needed for the reaction are contained within the one molecule. When triggered, they just reconfigure and shift into reaction products that again have less energy, are more stable, and as a result, you get a lot of heat release. Because the decomposition reaction is a single step, it tends to be faster than the burning types of reactions, although there is some overlap. For example, ammonium nitrate all by itself can be detonated. It can explode, but has a very low detonation velocity around 2,700 meters per second. The hydrogen and oxygen burning reaction that we performed a few months ago actually has a detonation velocity upwards of about 4,000 meters per second. So there is some overlap, but in general, decomposition is fast, burning is slow. A third way of dividing up explosives, and that's what we're going to talk about today, are called binary explosives. Now you might think binary, two parts. They're not burning reactions. The primary ingredient, whether it is ammonium nitrate, little prills, or whether it is the liquid Nitro Methane, both of these components actually can be detonated all by themselves. They are, in fact, explosives. But because they are so darn inert, it's almost impossible to trigger them. And as a result, they are sold and can be transported and stored as if in the one case it's considered to be an oxidizer, and in the other case it's considered to be a flammable liquid, like rum. This is a big important difference with this type of explosive, because until you sensitize it, because they are not considered explosives, the stiffest, the tightest regulations, the legalities of working with explosives are most restrictive on storing and transporting, not so much on detonating or fabricating. So as long as you leave them separate, you can handle them much more safely as well as much more conveniently. One of the most common, or actually the most common explosive in the world is called ANFO, A-N-F-O. It stands for ammonium nitrate fuel oil. The fuel oil, a few percent, added to the ammonium nitrate prills, sensitizes it to the point that it can be detonated. The reason it is so popular or so incredibly prevalent is because, first of all, it's extremely cheap. Ammonium nitrate is fertilizer. It's almost dirt cheap. But the second reason it's very popular is because it has a combination of a lot of energy output, twice as much as TNT, but a rather low detonation velocity. It's high enough to crack rock and break structures, but it doesn't waste all the energy like TNT would to send out a Mach 20 shockwave or shrapnel. Most of the energy available when it is detonated is available for pushing and slumping rock. So it's very popular in demolition and in mining applications. Now, the material that I showed you here, which is a commercial product called Tannerite, is familiar to anybody who's ever gone into a gun store or any kind of an armament distributor. They will often have these at the cash register. You can buy little packs of these ammonium nitrate and sensitizers that you can buy at the store. You can put them in your car. You can drive out to the range. You add, in the case of the aluminum powder, which is the sensitizer for Tannerite or Sure Shot, another brand name, you put it into the container. You mix it around for a couple minutes till all of the prills are nice and gray. Put it down range, and then you can fire a rifle bullet at it, and it will detonate. It's so insensitive, though, even once it's been sensitized, that you can't generally put this off, or you can't set this off with something as slow as a simple 9mm or a handgun. You often need the velocity of a rifle shell. So sensitivity is sort of a relative thing. Now, the reason you're able to do that is because it's a binary. You can bring it in your car. You can bring it to a location. You can mix it and use it. But once you've mixed it, it's considered a high explosive. So you either use it or you dispose of it, but you do not put it back in your car. You don't bring it back home. You got to get rid of it because now it's a high explosive. Now, what I'm going to talk to you about today, and we're going to spend our time demonstrating, is a high explosive based on nitromethane. This is nitromethane. And it comes in small bottles, liter bottles. You can buy it by the drum. And anybody familiar with nitromethane probably has first come in contact with it because it is a common fuel used in top fuel dragsters and as an additive for a fuel in RC airplanes. The reason it is because it's a fuel. It actually will burn in air. But because it contains about 2/3 of the oxygen it needs to burn it, you can use a lot less air to consume this fuel in an engine. And because the energy or the output of an internal combustion engine is not limited by how much fuel you can squirt into it, but by how much air you can draw through it. So by providing 2/3 of the air it needs to burn, you can use a lot more of this. Even though it's got less energy than gasoline, you can use so much more of it that you produce more energy for a given displacement. That's why it's so popular. Now, interesting material. When I first saw it, I thought, boy, this is like water. It has about the density, the viscosity, the surface tension of water. It's clear, it beads, and it has a relatively low vapor pressure. So when you smell it, it's a weak, fruity smell. It's not very potent because of the low vapor pressure. And if I left this cap off of this flask and left it in the room for a week, most of this would still be at the bottom of the bottle. That's not true of gasoline or alcohols. It's a relatively low vapor pressure liquid. And as I'll show you later, not a very impressive fuel all by itself. Now, nitromethane all by itself is a high explosive, but it is so inert, it's almost impossible to set it off. And there are several ways that you can sensitize it. The classic way is to use this, ethylene diamine. This is the ingredient that was used in the Picatinny Armory to produce a high explosive back during World War II. This is why the name of this material is called PLX, or Picatinny Liquid Explosive. By using a small percentage of this or any other basic or alkaline pH amine, diethylene triamine, DETA is another example, this will create a high explosive and you're done. And what's nice about that is it's a liquid. I'll show you what happens when you add this material to this. The nitromethane is pretty benign, but the amine is pretty caustic, so you want to be a little careful when you're dealing with it. But if I take a small quantity of the nitromethane, I'm not going to be very precise in my percentages here, but it's enough to show you what's going on. And then I add a small amount of the amine to this. They both start almost clear, but as I add a small amount of this to here, you'll see that it becomes a bright yellow. This is now a sensitized high explosive. Done. That's one of the advantages of working with this material, is that it is a liquid. It will flow into containers. It can be pumped, flowed, and you can you can have it conform to the size of the vessel that you're trying to explode, or the crack in the rock that you want to fill. Now, the way this works is kind of interesting, using picosecond spectroscopy, in other words, extremely fast spectroscopy. What they discovered is that the basic amines will form and stabilize radicals, free radicals of the nitromethane, and they tend to absorb right around 550 nanometers, just basically the same color as the sensitized material. Those free radicals are far more sensitive to shock than the base material, and so this then becomes sensitive enough you could set this off with a high velocity round, or other methods that I'll show you in just a little bit. Now, there's another way that you can do this. It's kind of interesting. You can also sensitize this material, this nitromethane, with aluminum powder. Now, aluminum is very familiar to people who build rocket engine grains, or people working with pyrotechnics, because aluminum powder, or aluminum, produces an incredible amount of energy when it oxidizes. And when you take powdered aluminum, which in some cases is coated with stearate, a waxy material, or in this case, graphite for the German black, these very small few micron particles will, when suspended in the material because of their greater density, will actually create little zones where, when a moderately strong shock wave moves toward the aluminum, some of that wave will move backwards. It will be reflected. But because of its greater density, it tends to focus the wave through the material and form a high intensity shock wave just behind the particle. And also the waves that are passing around the outside of the particle diffract, and again focus to the other side of the particle. Waves is waves, and it doesn't matter if it's light or it's sound or it's a shock wave, they behave the same way. And these concentrated zones, millions or billions of them within the material, provide little localities where the sensitization has occurred, and that again allows this to be sensitized to the point that you can set it off. There's a third method that's used, and that is glass bubbles. These are the same hollow borosilicate bubbles that we used to thicken the epoxy mixture earlier on when we were showing you how to fare boats or fiberglass structures to make a paste out of an epoxy glue or adhesive. These hollow glass 50 micron spheres are very lightweight, and the way that they work is interesting. When a moderate shock wave approaches one of these fragile bubbles, it crushes the bubble, and the gas inside of the bubble is compressed. Now, there are two types of compression. One is called isothermal compression. When you compress a cylinder and the pressure goes up and the heat is released, if the heat can leave the cylinder and the temperature doesn't go up, the pressure doesn't get quite as high. But when you've got a very tiny little bubble and you're doing this process in a period of a few nanoseconds, the gas inside doesn't have time to release its heat into the surrounding environment. That's called adiabatic compression. And so the temperatures can reach thousands of degrees and the pressure thousands of atmospheres within these tiny little bubbles, these voids. And it's the same process that occurs in sonoluminescence, where when a collapsing void or bubble that's created by an ultrasound wave inside of water collapses, you can create plasmas, you can create localizations of very high pressures and temperatures. This again is a method of sensitizing. The differences between these are that the highest velocity, the highest retaining of the velocity of the raw material is if you just use the amine. It's up around 6,700 meters per second, faster than TNT and far faster than the ANFO or the Tannerite or the Sure Shot. That's one of the major differences. This is a very brisient high explosive. By adding the aluminum powder, we lower the velocity a little bit, but what we do is we add a potential combustible agent to it. And so if this explodes in air, that vaporized thousands of degree hypersonic velocity shockwave of aluminum vapor contacts the air and burns. And so it's sort of a hybrid of a detonation and a burning type of reaction. The net result is we double the amount of energy per gram by adding a small amount of aluminum to this, so you can get more power. What's interesting is it doesn't work if you put this in a borehole or in some container where it doesn't contact the air, but it does work if you put it underwater. At a high enough temperature and pressure, aluminum will burn in water. And so this is often used in packages or bottles or sacks placed underwater for underwater demolition or for producing sonic booms for mapping purposes. The bubbles do not add anything to the velocity, and as a matter of fact, they rapidly decrease the velocity. And so what you can do by using the bubbles and or the aluminum and or the amine, you can dial in exactly what kind of explosive you want, how much power you want, what kind of velocity you want. It gives you a lot of freedom to be able to control the type of explosive you're going to build. Now, one of the problems you've got though with the aluminum and the bubbles, I'll show you right now. If I take the nitromethane and I pour a small quantity into this beaker, and I pour some in here too, and then I add some of the aluminum powder to one, and I add some of the bubbles to the other. Nothing precise about this operation. And then I stir them up a little bit to get them to mix. And I do the same thing with the aluminum powder. And then I set these down over here for a short period. You'll see a problem develop. The problem is that you can see it more clearly with the bubbles and a little bit less impressive with the aluminum, is that because the aluminum is heavier than the nitromethane and the bubbles are lighter, they tend to float out of solution. Obviously, it doesn't dissolve the glass or the aluminum. That's no good. They're not going to function. So in order to keep these materials in suspension, we have to thicken the nitromethane, and there's a couple of ways to do that. The most commonly reported way to do that is to use acrylic, polymethyl methacrylate, PMMA, lucite, plexiglass, shavings from a drill, or in this case, small little beads of extruded for extrusion purposes for forming plastic components. Or if you're very secure, you can go into a cosmetics shop and you can get the small little vials of powder that are used for strengthening and making beautiful nails like mine. But in any case, if you mix this in, this will form a more jellied type of mixture. If you look at this, this is 8% PMMA in this left-hand vial, and this is just the pure nitromethane. It clearly becomes more syrupy. But because of its low potency, you have to add a fair amount of this before this will settle out. And so another method that's very popular is to use nitrocellulose. It will dissolve in the nitromethane, and you'll get a nice jelly that will support these powders. Problem with that is then you have to format or you have to formulate another explosive, and it kind of undermines the advantage of a binary. So what I came up with, which I haven't seen actually reported anywhere, but actually works quite well, is food-grade methyl cellulose. This is the same sort of thing that you would add to meringues to turn them into marshmallows. It can thicken icings, and it's what we use in our secret sauce for our super duper bubble machine that we're going to be showing you in a couple months. But this material will actually dissolve and create a nice jelly with a low percentage, and let me show you how that works. Now over here on this little mixer, I have some nitromethane, and I have some of the methyl cellulose right here. And you'll notice if I turn on the mixer here and I place this powder in here, you'll see that it forms sort of a milky suspension. Problem is, you could leave this on room temperature, leave this for days, and this won't dissolve. It doesn't dissolve in the pure nitromethane, but it does dissolve in the sensitized PLX, or the amine sensitized material. And so if you add a small amount of that to the nitromethane and the snow that you've sort of formed by adding the powder, it will gel up. Now we'll give that about 2 minutes. All right, that's looking pretty good. So I'm going to go ahead and turn this off. And we'll get the magnet out of here. And now this is nicely thickened. You can see it's jelly-like. One little trick, though, to keep in mind is that if you add the amine to the nitromethane first and sensitize it, and then you put in the methyl cellulose, the outside will lock up and you'll have a nice big dumpling rolling around in here, and it'll take about a half hour to 45 minutes longer to dissolve this than if you put the methyl cellulose in before you sensitize it. Now this material here, I'm going to add to a little container, and what we're going to do is we're going to mix in some of the other sensitizers. So I'm going to turn on the scale, and I'm going to add about 10 milliliters, which is very close to 10 grams of this material into here, if I can do it with this little very short dropper. This could take a little while. That's pretty good. A little long, but we'll keep it there. Now, I'm going to add to that some of the aluminum powder, like this. And I'm going to add some of the bubble powder, triply sensitized. And then using the back of my spoon here, I'm going to mix this stuff up. And what you end up with is sort of a thick gray paint. And as soon as I mix this up, I'll show you what I'm talking about. Now you might think, oh, be careful. This is triply sensitized high explosive. And it is. However, sensitivity is a relative thing. I'm going to show you what I mean by sensitized. All right, now what I'm going to use is some of the double base powder, and we're going to take 50 milligrams of this, put it on a little aluminum foil tab, and with this we can then get an idea of sort of what the baseline explosion looks like from a given quantity of just the triggering explosive. Tiny bit more. That's close enough, 49 milligrams. Now, if I can be careful and set this here over onto the plate, and then what I'm going to do is I'm going to cover this with a small piece of aluminum. This seems to keep it from spraying out when I hit it. And then This is not that impressive, but if you do wear headphones or are using headphones at a high level, you might want to turn down the volume. All right, here we go. So you can see it does explode. This stuff does work. Now what we're going to do is repeat that, but we're going to use some of the TIX. Close. Now before I set this down in that spot, I'm going to add a little bit of the TIX to it. Just a couple drops. I'm going to put this over the top, like this. Okay. And then to keep it from spraying, once again, we're going to use the aluminum. Same amount of smokeless powder. And if you do have your headphones on, now you'll probably need them. Okay. 1, 2, 3. 3. No question, the stuff works. And it does make you smile. You can't help it. Now, what's interesting about that is that it was a long-standing controversy for many years as to what actually explodes when you set a shock wave into a material. Is it the heat or is it the shock wave? And the reason that was so difficult is because they're intimately related. You release heat in a very short period of time, you get a shock wave. If a shock wave hits a surface, you get heat. So is it the chicken or the egg? Which came first? And interesting thing, if anybody ever asks you that riddle, which came first, the chicken or the egg? Well, the best answer I've ever heard for that is that it is an egg with a chicken in it, because the greatest amount of mutation occurs during the formation of the zygote. And so it was 2 non-chickens that bred to form the first chicken in the egg. But I digress. The answer came when they developed femtosecond lasers, and they were actually able to irradiate a small sample of high explosive with such a short pulse of light that they could heat the individual molecules without allowing them the time to even move. So shock wave was not part of it. And regressing the amount of energy necessary, it turned out that it was the heat that actually did it. So if anybody ever asks you that question, it's the heat, it's not the shock wave. But because they're so intimately related, and because this is the only way we can develop either one of them, we develop them as a pair. The question then is, what if you want to set off more of this? Obviously, if I'm going to put off 100 grams of this stuff, I'm not going to do it with a hammer. I'm going to need to step back. And typically what would be used is what's called a blasting cap. Blasting caps are based on a high explosive called pentaerythritol tetranitrate, PETN. And it is a relatively sensitive high explosive that a hot wire is able to trigger. And then its explosion then transfers into the medium the charge that you're trying to set off. Problem with blasting caps is, number one, they're very highly regulated. You can't get a hold of them. Number two, they are dangerous. You could blow a finger off with one of them. And blasting caps are also rated in terms of their overall force. They're called, say, number 6, number 8, number 4. And the number stands for the number of milligrams of the PETN that's used. Obviously about 20 times as much as we used in terms of the smokeless powder. And so when you hear an explosive that's designated as cap sensitive, they mean a number 8 cap. That's sort of the industry standard for making the division between cap sensitive and cap insensitive. Now, because I can't get a hold of those and I don't want to set off a large charge with a hammer, we're going to take advantage of high voltage and electronics to actually turn a very small piece of copper wire into an incredibly powerful explosive. It can produce thousands of times more energy per gram than the most energetic high explosive. It's actually intermediate between nuclear and chemical explosives. And by doing that, what's called an explosive wire detonation, we can take advantage of having something that is entirely inert until you charge the electronic equipment. But once you do, you can then set off the high charge. And so when we go to do that, what we will do is we're going to be using a setup. I'll show you a little hint of what's going on here. that involves a capacitor, high voltage system, and an exploding wire behind a bulletproof laminated plastic shield. The reason we're not going to do that today, go outside and set this up, is because we're waiting for the delivery of a very high-speed camera from a company in Canada. And this newest model of their camera can record thousands, tens of thousands of frames per second at high resolution. And because of the fact that we think this is going to be much more interesting to see when you can see the actual explosion developing over time, we thought it made sense to wait for that until we get to that camera. We're going to hold off on the outdoor experiment. So hopefully the information that I gave you here is useful. Again, I'm not trying to give you a formula on how to make these things. I'm just trying to tell you how they work. And the information is obviously out there if you're that curious. But again, my warning is don't mess around with explosives at home, even if you feel you're comfortable with chemistry. I hope you like the video. And if you like the kind of content that we have here, please subscribe, hit the all notifications. It helps us to grow the channel. It helps YouTube to recognize us and give us the time to maybe promote some of the things that we're doing. If you liked what we're doing, give us a thumbs up. And if you have a comment, suggestion, or question, put it below the video because I read them all and I try to answer as many questions as I can, and it gives me ideas for new videos as well. So I'm going to wish you a very happy and safe weekend, and for those of you in the United States, a very happy 4th of July. You take care, and we'll see you soon.